All right, well, good morning, everybody. Welcome to the North Carolina Maritime Museum's lecture series. My name is Michelle Crepeau, and I am the conservator for the North Carolina Maritime Museum. If anyone here does not know what a conservator is, you can think of me like an artifact doctor. My job is to essentially take care of the artifacts that are in the museum's collection and attend to any health issues they have while they're with us. That means things like doing chemical interventions to make sure they're more stable in their environment, helping to control the environment to make sure they don't fall apart, and also trying to repair them and look a little nicer when they start to do. So today I'm going to be talking to you about a subject called electrolytic reduction, which is an electrochemical technique that we use to try to stabilize artifacts that have come from a burial environment, particularly one that is an underwater or maritime burial environment. And this presentation seeks to essentially explain why we sometimes stick electrodes on things, why sometimes you'll go places, see things in big tanks with batteries connected to them, and sort of give you an overview of how that works, what we do, and sort of the benefits it provides to the artifacts. There will be some science in this. I'll give you some background in terms of what electrochemistry is and kind of the basics of how galvanic cells work versus electrolytic cells, and sort of what's going on sort of a molecular level that is allowing for this work to be done. So to begin, just to kind of give a couple definitions, electrolytic reduction, sometimes annotated as ER in some of the literature, you may see this on some signage and interpretation at the museum and elsewhere, essentially refers to a type of electrochemical process. And the easiest way to kind of interpret what electrochemical processes are is to think about types of energy and the movement of different types of energy. So there's all kinds of different types of energy. There's heat, that's a type of energy. Light in sunlight, for example, is a type of energy. And we also have electrical energy and also chemical energy. And electrochemical processes are processes that have to do with the relationship between electrical energy and chemical energy. And at its core, what they both are talking about the movement of these subatomic particles you may have heard of called electrons. So it's all about the movements of those electrons and how those are able to cause changes. Electrolytic reduction, if you want to get a little bit more into it, is actually a type of a process that we call electrolysis. Some of you may be familiar with that term as well. Electrolysis comes from the Greek, where lysis means to essentially untie, unbind, break apart. So essentially it literally means using electricity and electrons to break something. In this case, it is chemical bonds between types of matter. And essentially we can also use that type of energy to perform other types of work as well. So we can direct that energy, that electrochemical energy, to do things like transfer matter, stabilize things, etc. So kind of give a basic overview is electrochemical reactions happen in a certain contained environment, which we call a cell. So in order to have an electrochemical cell form, what you need are certain pieces. You need two types of different materials. So these materials can be different in a variety of ways. Usually they have differences in their atomic structure. They have differences in composition. Usually they're types of metals, and they can be alloys. In that terms, they can be different alloys of the same base metal, for example. They can also actually form on the same piece of an object made of the same type of metal due to slight variations in composition as well. And these are all underlying differences that contribute to the one difference that we're really interested in, which is looking at differences in electronic potential. And this can be understood very simply as the propensity for material A and material B to pass energy between each other in the form of electrons. And there are they polarize into essentially two components, an anode and a cathode. So you may be familiar with that terminology, we'll get into the definition of what those are in a little bit. And then there's also the fact that these two materials, so we have two different materials that are electronically different, they polarize in different ways. One becomes an anode, one becomes a cathode. They transfer electricity between them, and they do that through 2 points of connection. So they need two different types of connection. One of them is they need some sort of physical connection. Sometimes they're literally just touching each other. Sometimes they're being connected by a wire or another type of conductive medium that is holding them together in a physical way. And then the second type of connection is that they need a conductive medium that also connects them. So in a conductive medium, it can be a gas or a liquid that contains these things that we call electrolytes. So some of you might be familiar with electrolytes. It's in some sports drinks and liquid IVs, and your doctor might tell you need more electrolytes in your diet. So we are familiar with these on kind of a conceptual level, but what are they in actuality? And essentially, electrolytes are charged particles. So they are charged atoms or charged molecules. Essentially, they are small pieces of matter that have an electronic charge associated with them. And they come in two forms. We have cations, which are positively charged, as well as anions, which are negatively charged. And the charge comes from differences in electrons. Essentially, cations have too few electrons, anions have too many electrons, which makes them negatively charged since electrons are themselves negatively charged. And essentially, these don't exist in a constant state. They are in constant flux. It is dynamic. They are constantly essentially passing that electron along between themselves, like a relay race, you can think of it as, in terms of they are forming bonds with each other through these electrons. They are forming bonds and breaking apart our two materials that they're in contact with. This is what we call chemical energy. Essentially, chemical energy is electrons being passed back and forth by subatomic particles or molecules. So it is happening, sort of basically being conducted with sort of a buddy, a partner that's actually doing the conduction. With the exception of sort of this, I guess, relay race metaphor is that, instead of baton, they're carrying electrons essentially. And as I kind of mentioned before, there are two, these points of connection are important because they're essentially form pathways for energy in the form of electrons to go from one material to another. So for example, this is what we call chemical energy when it's happening in the electrolyte. So as I said before, that electron being passed through the breakage and formage of bonds between different chemical reactants is chemical energy. And then the conduction of essentially free electrons through a physical medium, like this wire up here, is what we call electrical energy. So there's 2 points. There's an electrical connection and there's a chemical energy connection. And in most types of electrochemical cells, this chemical energy is what's driving the reaction that's happening. And it is also directional. So we have chemical energy that is happening in our electrolytic solution that is essentially forming bonds and breaking bonds in our anode material. So in that this material over here, that anode material is then essentially breaking up into pieces and also releasing free electrons. And our conductive physical connection over here conducts those electrons in a pathway that only the electrons themselves can go through. So that is what we call chemical energy. Whereas in the electrolytic solution itself, and there is a direction towards that, let me just kind of emphasize that. As you can see, the electrical direction goes from the anode to the cathode. So that is the direction, and that is based on those differences in electric potential, which we'll go into in a little bit more detail in a bit. There's also movement, as I mentioned, in that electrolytic solution, that chemical energy. This is also directional. As you can see, your cations tend to be pulled towards the cathode, your anions tend to be pulled towards the anode. And it is this interaction, particularly between your anions in solution and your anode, that is creating the chemical energy, that is breaking bonds, and that bond breakage is what's releasing electrons that are then flowing through your conductive material that is connecting them physically. And the end result is essentially you get this flow of electrons from one material to another through this physical connection and then into this conductive medium. Around and around it goes, so to speak, until there is essentially nothing left of our anode material. And this you might recognize as essentially what an electrical circuit is. And like most electrical circuits, we can essentially take advantage of this and harness this electrical energy to do work for ourselves. For example, creating light, creating radiation, essentially sort of diverting that current into something else, causing another sort of like incandescent reaction, for example, to produce light, and without necessarily disrupting the circuit, but just sort of adding on to it and sort of using this electrical energy to do work for us. This is also how a battery works. Some of you are familiar with how this works. You have your two different materials You have your cathode and your anode material. Usually lithium and graphite tend to be what's in most batteries. You have your conductive medium, your battery acid, for example. You have a circuit that is created when you plug the battery into something, essentially like a flashlight, that creates that physical connection. Some of you might have also done this experiment sometimes in your life, using your potatoes. This is often done in a lot of high school science classrooms. This is essentially making a battery. You are making an electrochemical cell. You're using the potato essentially as your conductive medium, because potatoes are nice and starchy. They have a lot of little electrolytes in them, a lot of nice good anions and cations to help conduct and sort of set off those chemical reactions. And you'll also generally put two different types of metals, in this case zinc and copper, that are then physically connected by a wire. And as you can see by this voltmeter, you are actually producing electrical current from a bunch of potatoes and nails, which is pretty cool. And these types of cells we call galvanic cells. So galvanic cells are kind of the most common type of electrochemical cell, because they are the type of cell that forms under most atmospheric conditions. So under most conditions that are available on planet Earth that we encounter in terms of things like temperature and pressure and, pH, in terms of acidity or alkalinity, in terms of oxygen content, this just tends to be the type of cell that forms natively. And just to go into this a little bit more, they happen what we call spontaneously, which means they happen without they happen on their own accord, essentially, sort of naturally, without any other type of energy or any other type of conditions sort of having to be artificially met to drive this reaction. And what we have here, just kind of going into a little bit more of the parts of a galvanic cell, you can see we have our two different materials that are represented by zinc and copper. Maybe you also did this experiment in high school as well. You have two different metals which are in electrolytic solutions. Maybe they're in the same beaker, maybe they're connected by a bridge that lets that electrolytic medium sort of cross over, and then they're usually connected by some piece of wire. And so a lot of us probably did it in this. And what did we observe when we did this experiment in high school? Well, we observed maybe we had a voltmeter on top of it, so we could actually see that it's registering a current, but we also saw physical changes happening to both our two materials. You might have noticed that the anode material tends to break apart and dissolve, whereas the cathode material tends to get stuff precipitating on top of it. And this is because what's happening in terms of the chemistry is that at our anode, there is a process happening called oxidation. So oxidation is what happens when you have anions essentially taking electrons from material like our solid zinc metal here and breaking it up. It's then creating both basically zinc cations as well as electrons. And these free electrons are then able to be conducted out of the material across the wire and into our cathode material, which is receiving them. And at the cathode, what happens is those electrons are being put to use. So the electrons are important because they are basically what holds subatomic particles together in terms of molecules and in terms of atoms. So like all our molecular structures, they're being held together by connections that are created by this energy that is created by the presence of electrons. So you are essentially putting electrons into this system, and the system is essentially using those electrons to make new bonds with things. It is creating matter. So that is why you have precipitation of material at the site. You actually have the growth of the material, if you would. And this is essentially all through because of this transfer of electronic energy based on chemical reactions. And this is determined, and kind of going back to the idea of electric potentials, which I sort of talked about a little tiny bit in the last slide. This is based on the fact that they have different electrical potentials. And what this means is that it can be thought of as a lot of different ways. Sometimes it's described as the electrochemical series. Sometimes it's described as electromotility series. In this case, since when it's talking about one-on-one, we usually call it like kind of one-on-one reactions between different elements or atoms. We talk about the electromotive system of series, but when we're talking about cells, we call it the electropotential series. And essentially what it is it is a measure of how likely a particular type of material is to either give up electrons or receive electrons. Essentially, how likely is it for this material to be an anode versus a cathode? And it uses hydrogen as sort of the baseline, so that'll be 0. And then it is either more positively charged than hydrogen or more negatively charged than hydrogen. I won't get into that too much. But essentially what you need to know is that things that have a higher electrochemical potential are more likely to become anodes, where things that have a lower potential are more likely to become cathodes. And this is sort of the innate chemical properties under most conditions that we find on planet Earth that direct the direction of this reaction and drive it. If anyone has any questions so far, please do ask. And this is the type of chemical activity that is happening in your batteries, whether man-made or in your excuse me, or in your potatoes. And just sort of kind of zooming in a little bit further, these reactions, this transformation of material where one is essentially broken up and dissolved and the other is built up and new material is created, is what we call an oxidation, is called a redox reaction, or is sometimes called a redox reaction, standing for reduction and oxidation. And essentially what it is I've kind of described before, is that you have two compounds on a molecular level or on an atomic level, in which there is a transfer of due to differences in our potential, there is a transfer of electrons from component A to component B, as you can see over here, which then basically is what allows things to happen. It creates our ions, which are then able to go and become electrolytes. It also is what creates opportunities for new bonds to form. So that's kind of the salient point of that. We can also, again, sort of hijack that chemical energy to produce electrical energy, as the case with batteries and light bulbs, etc. And then since I've been talking a lot of time talking about galvanic cells and a lot of times talking to you about redox reactions and spontaneous reactions, whereas there are also non-spontaneous reactions. We can't actually make this happen, as I've been kind of repeating again and again. Under most natural conditions, spontaneous reactions are what you get, but under very specific conditions, we can essentially game the system, as you were, and essentially force redox reactions to go in reverse. So we can actually switch who the anode and the cathode is in a reaction, and we call these non-spontaneous redox reactions. We do this essentially by inserting electricity into a system. So we use electrical energy to then essentially drive chemical changes that can then sort of result in reduction and dissolution happening at sites we would not normally get. So what this looks like, and this is what an electrolytic cell is. So an electrolytic cell is what electrolytic reduction is based on. So just for an example, so we have our metal over here, silver. We also have a fork over here, and this fork might be made of something like steel or copper or something that has a higher electronic potential than silver does. Because you remember that chart that I showed you a couple slides ago, silver was all the way down on the bottom of that chart. So it is not very likely to give up electrons without some incentive, essentially. So what happens here is that we still have our two different materials. We still have our conductive medium that is full of electrolytes, and we still have some sort of physical connection. But as you notice, instead of this just being a continuous circuit, there is directionality to it. And this is actually an electrical source, so a DC battery or some other type of electrical source that can provide energy. And what it's doing is it essentially is using electricity to actually forcibly break the bonds in our silver piece over here, and then draw out those electrons, and then essentially transfer them down to our cathode material. So it is essentially forcibly interfering in what would be a natural flow and sort of redirecting that flow to get a different result. And the result is essentially that we get an anode that is usually not an anode, that is dissolving and producing cations in solution that are then, and a cathode, which was not normally a cathode, essentially being a site of reduction instead of oxidation and essentially creating new material. This is also the basis for electroplating. So essentially electroplating is a very kind of more well-known type of electrolytic reduction in which you are driving a reaction that would not normally happen by adding electricity into a system that then creates a chemical change in something. And just to sort of reiterate, the difference between our galvanic cell is that you have a direction which is going from an anode, which is a higher electronic potential, to a cathode, which is a lower electronic potential. You have a site of dissolution happening at your anode, where you have chemical energy essentially taking apart this material that is being transferred into electrical energy, and then being used to basically make new bonds and build new material at your cathode. Whereas, and you can sort of see that illustrated here and here, so you have dissolution happening, and then you have precipitation and basically plating or buildup of material at your cathode. Electrolytic cells, it's happening in reverse. And you sort of get the opposite outcome. And as you can imagine, this could be pretty useful when we're trying to, say, deal with corrosion. Corrosion itself is a galvanic reaction. So corrosion of metals from archaeological materials is a result of corrosion in that environment, and essentially the transformation of what is a solid metal material that is mostly made of the same type of material to one that is made of a mineralization process. It's a transformation from a metal into a mineral of iron, for example, and its other constituent parts. So you can imagine that having something where we might be able to actually reverse that galvanic cell and actually maybe produce metal even from corrosion product would be kind of cool. All right, so now we get into why do conservators use electrolytic reduction? How do we harness this energy to do work for us? So what do we conserve? I think I explained a little bit that we often we use electrolytic reduction specifically to conserve metals, specifically metals that have been in a burial environment, which has caused them a lot of corrosion, or which we have a lot of problems with soluble salt contamination, which, if you can imagine, the ocean is pretty salty. So any type of conservation that is performed on artifacts from a saltwater environment like the ocean often goes through some form of electrolytic reduction if it's a certain type of material and if it's robust enough, meaning if it's sort of strong and sturdy enough. And we use it to do several things. We use it to actually help remove a material on the surface of these artifacts called concretion. If anyone has visited the Maritime Museum or visited any type of maritime museum which might have artifacts on display which are sort of unusually encased in this dense concrete-like material, that is something that we can actually use electrolytic reduction to remove. So we can basically use it to clean artifacts and remove this sort of overburden, this burial environment accretion from the surface. We can also use it to physically and chemically stabilize the artifact by using that sort of reduction and reverse process to essentially kind of reverse corrosion in a way and sort of shore up our artifacts. And we can also use it to help aid and drive in desalination. Desalination is a treatment that we use particularly on things that are waterlogged, they're from underwater environments or flooding tidal environments, especially ones that have a lot of salt in them. That salt ends up inside the artifacts, and especially if you've ever lived on the coast, which I think many of you have, you can tell that salt is not always great for metal artifacts, is it? Like how many of you have kind of seen metal infrastructure on the coast just sort of weathering away due to contamination by salt in the air and salt in our water. So desalination is a method that we use to essentially draw out those salts and remove them from inside the artifact, thereby kind of slowing down or curtailing a lot of continual degradation of the artifact. And I'll get into a little bit, but I'll explain how electrolytic reduction can actually be really helpful in this process as well. So to begin, how do we clean artifacts? So we clean artifacts based on the principle that at your anode and cathode, you're not just reducing and oxidizing the metal, the two different materials that you have as your cathode and your anode. You're also sort of doing similar things to the immediate environment around the artifact, around these two materials as well. And as a result, you are producing gas. You are producing mainly oxygen at the cathode and mainly hydrogen gas at your anode, or excuse me, you are producing hydrogen gas at the cathode and oxygen mainly at the anode. And these gases can be both beneficial and detrimental to the process, so we also have to make sure we control them. But sort of how it works is that you have production of hydrogen gas at your cathode, represented by these little balls, which then basically expand in volume, they exert pressure, and they can actually, these little gas bubbles can form or get caught in spaces between the artifact surface, which is right here, and our overburden, our concretion, whatever we're trying to remove. And they can actually be used, that pressure, to essentially pop off that material. So they can be used to some degree to help clean artifacts from an underwater environment, and actually do it pretty quickly. There are downsides to this, which we'll get to in a little while, but it is a technique that sometimes electrolytic reduction is used for. It's not actually necessarily aiming to reduce our artifact. It is aiming to reduce the area around it in order to produce hydrogen gas, in order to create this sort of gas evolution and this removal of this material that's not really desirable to have on our artifacts because it gets in the way, we can't see it, we can't access it, et cetera, et cetera. Another thing that it's used to do is that reduction reaction that I've spent a long time talking to you about is also used to essentially transform a surface of our metal artifact that is covered in different types of corrosion products. It might also be a very fragile surface. There might be a lot of cracks in it. The surface may not be very well adhered to the surface or very stable, which obviously we want to try to consolidate that and make it more stable, both in terms of so it doesn't continue to react with the environment, in terms of being a lower electronic potential than some of these mineralized corrosion products tend to be, as well as to try to shore up some of these gaps and breakages in this very fragile surface. And how we do that is we add electricity, we create a cathode out of our artifact, as you can see, that produces electrons, which then essentially create new bonds. In this case, it creates solid metal, which is then depositing on the surface. So then we kind of fill in the gaps. It also is basically transforming some of these corrosion products into solid metal, redepositing them on the surface. And it's also transforming some of them into slightly more stable forms of corrosion, like magnetite is a good one. And this transformation process will also kind of fill in those gaps and help hold the surface together. So it creates a surface that is both more stable in terms of it's not as reactive. It doesn't have as high an electronic potential to keep reacting, to give up electrons, et cetera. It's a more base steady material. It also can help aesthetically, and it also helps keep the surface intact. And how it also helps mediate desalination. So desalination, as you can see, here's our base metal right here. We have our chloride ions. Chloride is part of sodium chloride, which is the salt, our table salt, the salt that is found in the ocean. This is the most kind of pernicious type. This is the most common type of salt that we have really encountered. It also has the most pernicious effect, especially on metal artifacts, especially on iron artifacts. You can get a lot of really nasty types of corrosion products and a lot of really kind of damage to these artifacts that is hard to control unless you remove them. So normally how it works is that we desalinate based on diffusion. So diffusion is sort of the movement of some type of particle to an area where it is, from an area where it is overrepresented to an area where it is underrepresented. This is called a diffusion current. So in this case, it is more highly concentrated inside our artifact than it is in the medium that is in. So we do this essentially by putting it through a series of freshwater baths. And because there's less salt typically in the water than in our artifact, it is naturally drawn out through diffusion. And it follows a concentration gradient, which is just basically based on the amount of chloride you have. But it can also, and until it essentially hits an equilibrium where you have equal amounts on either side, and that's equilibrium. It can also follow electronic gradients on the idea that you have a lot more charged ions inside of your artifact than you necessarily do in the water. So you also get sort of electronic gradient where the negatively charged chlorides are attracted to the relatively positively charged space of the water bath that they're in, which would also kind of perpetuate, which would direct that current out of the artifact. However, you also tend to have a lot of other things in water. There are a lot of other dissolved anions and cations in that water. There's biological things. There are a lot of things that can make this gradient a lot harder to enforce, because obviously the less of these sort of competing ions we have, the more efficient the gradient in. There's less competing for those gradients, and the faster desalination will essentially happen, because if not, desalination will keep hitting that point of equilibrium, and we'll keep having to change it out, wait some more, change it out, wait some more, etc. So this creates a bit of a problem. But we've just, especially since over time, you then also tend to get other types of cations and anions trying to get inside your artifact as well, which can't be good. And it'll also reach a state of equilibrium where desalination will also kind of shut down. And the more of these types of particles you have sometimes, occasionally the faster that can happen. The exception is, however, when you have cathode material, when you use these dissolved anions and cations in your water bath as electrolytes and create an electronic cell. Because then all of a sudden you have a polarized current that is happening inside between the cathode and your anode. So you have charge that is then directing the movement of cations and anodes and anions. So you have your anions being, and your anions are going, like your chloride, are going to be more attracted to your anodic material that you have in your cell than they will be to their cathodic material. So they'll be like basically it's essentially putting energy into the system in a way that essentially drives diffusion faster. So this is a good way to speed up diffusion and also make it more efficient. Does the distill water? It can. It can. Obviously, different types of filtration processes for different types of water remove more or less or different types of materials that is dissolved in the water. Distilled water does help. Distilled water really is good at filtering out some ions, but mostly it's really good to filter out biological material that is in your water. We have other types of filtered water that we will use, reverse osmosis water, for instance, or even deionized water, where you have increasingly more specific amounts of our cation and anion content, basically our hard water, essentially, are essentially filtered out of what you get. So obviously having a pure medium, you have a lot more efficient, faster gradients. But sometimes it can't always be done, especially if you're working in large quantities. If you have a huge tank that has a can in it, for instance, making that much RO water or distilled or deionized water, or even distilled water, may not be worth it, just because you do have to change out these baths on occasion. So having to replace that constantly and is not always cost effective or resource effective, which is another reason that electrolytic reduction is often applied, because even in just tap water, it can still help make a more efficient diffusion gradient by introducing this polarity and sort of driving our anions, especially our chlorides, out of the artifact and away from it to our sacrificial anode, which we'll get into a little bit more. Does that answer your question?
Yes. So your answer is using electricity to keep it away.
Sometimes. I mean, and obviously the best solution is to use them together. But you would have to have kind of, depending on the size of your operation, you may need to get like an industrial size RO system, for example, to produce the amount and volume of water that you need to do that. But usually some combination is kind of the best medium that we try to aim for, as long as resources allow for it. So, but using electrolytic reduction is another way to sort of overcome sort of the stop and start of desalination and make it more efficient and make it faster. Electrolytic reduction can actually reduce desalination, especially of large cast iron material that has come from the ocean, by decades sometimes. Like it can take something that would normally take 10 to 20 years, and we can get it out of desalination within 5 or 6, which is amazing when we're talking about sort of the scale of the kind of the time scale of archaeological. It can, yes. Yes, it can. Also, you know, sometimes there's some times where electrolytic reduction is not appropriate. We'll get into that a little bit. We usually use electrolytic reduction on more robust metals, so particularly like cast iron or even wrought iron, but it has to be really solid, because wrought iron can actually be very fragile. It often doesn't survive in ocean water very well, just because of how it's manufactured. There's more impurities in it, and also just it has a grain structure because it's folded over, hammered, folded over, hammered, so it has a grain structure that capture impurities and things in them, and it will often kind of split and fall apart along these grain structures. So sometimes introducing energy into that system actually damages the artifact because it's too powerful, and essentially you can exacerbate like tiny cracks and weaknesses where those grain boundaries are. All right, so variables that can affect the efficiency of your electrolytic reduction. So what are sort of the variables that you choose when you're looking to set up an electrolytic reduction setup? So a lot of it has to do with the setup of your treatment itself. A lot of this has to do with where you're placing your anode, because usually what happens is you have your artifact, which is you want to be your cathode. That is what you want to be reduced. That is what you want to use that electrical energy for to do some sort of work that can essentially make your artifact more stable, that can keep it together, that can help desalinate it. In order to do that, you have to have something to act as your anode. And because you don't want your artifact to act as its own anode, which can happen sometimes, you usually have to have what we call a sacrificial anode. So some other type of material, usually mild steel or something, will go into the tank with these artifacts. It'll get the anode part of the gator clip essentially, and what it is, selection of that anode material, because you really do want to make sure that it is something that will work in the system, that it has, it has a lower cathodic potential, it has a lower energy potential than your cathode, for example. And also where it's placed. Where it's placed is actually kind of a big deal, because that is essentially the direction that your current is going. So where you have your anode determines sort of the direction of that flow within the tank or within your treating medium. So that can actually affect how efficient the system is too. We'll get into that in a little while. Also your power source. There's a lot of things about your power source you want to get into when you're sourcing one. Generally we use DC power. You want something with a good ripple, something that you can really kind of control that conversion between AC power outlets and DC energy pretty well and keep it pretty stable, for instance. Also, how many you have and how it's attached to your artifacts. We'll get into that in a couple minutes. Current density is another big factor, as are the concentration of your electrolytes and the pH of your conductive medium as well. These are all things that can affect how well your cell is maintained, and basically keep that cell intact, because it can pretty easily break down since you're essentially fighting against nature to have it in the first place, and also keep it efficient so that it's kind of worth the resources and the energy that you're putting into it. And of course, these will all ultimately, yes. And so this is an example of a common setup that you might see if you visit an archaeological conservation lab where they're doing electrolytic reduction, for example. So we have our tank. Generally, you want something that is, of course, itself non-conductive, because you don't really necessarily want the tank drawing energy away from your cell and itself becoming either a cathode or an anode. Although sometimes there are times where you actually do use the tank or the tank lining as the anode. I have seen that. So occasionally that does exist, but a lot of times they're made of wood with maybe a PVC liner. Sometimes they're made of glass, or sometimes they're made of a really high density plastic, for instance, that can obviously withstand heat. You have your anode selection here. We have 2 steel plate anodes on either side of your artifact here. This is where our oxygen evolution occurs. I said I'd get into why oxygen evolution was important as well. Oxygen evolution, you're basically aerating your system, and you're also making sure that it stays mixed and that everything stays moving. Instead of using like a pump, essentially, to make sure that you don't have water that is settling in place. Because what happens if you don't have a conduction or some type of current that is happening, you have a higher likelihood of your electrolytes deciding that they kind of like each other more than they like either the cathode or the anode, and essentially forming electric bonds with each other and precipitating out of solution as a solid, which means they're not in the solution to be electrolytes anymore, which is kind of a problem. So making sure so what happens if you have multiple anodes in your system, that is a good way to make sure that you have water movement as well, because it's being essentially propelled by this oxygen evolution, which is essentially churning up, keeping the water nice and mixed, keeping that water moving, making sure those electrolytes don't get too friendly with each other, and making sure they stay in solution. So that's one of the reasons why having multiple anodes sometimes surrounding your artifact is actually really beneficial. And this also helps, provides chloride buildup within your system. It also helps stop anything building up at your cathode or your anode that might otherwise impede the circuit that you're trying to maintain. These are some examples of some various types of setups we have. Kind of the ideal setup, if you can do it, is sort of a 1-to-1. We have one artifact in one tank. You have an anode that essentially surrounds it as much as possible, so that kind of you get the most out of it. You get basically the chlorides being pulled out in all directions, you have reductions happening in all directions, you have good oxygen production and movement of your water in all directions, and then having one power source that is basically you're getting the best maximum out of your power source. Unfortunately, this is the ideal, but it's not very often practical when you're an archaeological site, just because we are often dealing with many artifacts at the same time, many of them very small, many of them that all need to be treated, and it's not really efficient to treat them on an individual basis. We will do what we call batch treatments. So that's what these three setups or four setups illustrate, is different types of batch treatment methods. So we have multiple artifacts being treated together in the same tank. Again, ideally, if you have multiple artifacts being batch treated together, it would be wonderful if each one of them had their own separate anode, if they each had their own separate power source, so that basically that energy was being more efficiently directed to them and only them. Again, though, this is often very hard to achieve, especially if you have a lot of artifacts. It's not necessarily very resource or monetarily feasible. So usually you get setups more like what you have on the bottom, where you have, for instance, multiple artifacts that have one single power source. So you have one single DC power source, essentially, and they might be connected, and sometimes they might have their own leads, their own gator clips, essentially, that are connecting them to the source if the source can handle that, with an anode, kind of a shared anode that is shared between all of them. Or more commonly, you have this type of setup where you have a power source that is being directed to a single line of connection. So you have a single pair of gator clips, which are forming your circuit, that are then attached to a conductive medium that is then attached to your individual artifacts. And there's still an anode either on the bottom, on the top, sometimes on the side. Sometimes you will have multiple anodes. The problem with this, though, is that sometimes this current gets diffused and it loses energy the more artifacts it has to go through. So the more artifacts it is trying to essentially provide power for to drive this electrolytic reduction reaction, oftentimes the less complete or less effective it is, the further away from the energy source you get. Obviously, the artifact here at the beginning is kind of getting the most in terms of your electrical load. The one the furthest away is getting the least amount. So this, unfortunately, is efficient in that it is the least resource intensive, but a lot of times it is the least effective in terms of fully achieving the outcome that you want, whether it's to reduce and consolidate the artifacts or to drive desalination. And then there's this kind of modified version of this, which is kind of similar. The difference is that it has multiple leads, power source, and each one has, instead of having a shared anode, each one is kind of put into these little separate compartments that have their own anodes inside of them. So you can also get some variation of this. But this is honestly just the most common, just because it tends to be the more resource friendly for us. But it does mean that your outcomes can be kind of unpredictable sometimes. The other kind of big factor that determines the effectiveness of using electrolytic reduction to do work in archaeological conservation is our current density, which is very kind of simply put is a measure of the amount of electrical charge that passes through a particular area in a given amount of time. It is measured in amperes per centimeter squared. And it is essentially determining how much of amperage per centimeter square you need to effectively to be effective on your artifact is sort of a measure of the surface area to anode surface area ratio. And it is affected by a lot of different variables in its own right, electrical resistance, for example, and electrolytic concentration. Electrical resistance is essentially how easy is it for that electrical current to pass through a material? How conductive is it? Electrolytic concentration is obviously how many electrolytes are in your chemical medium to be able to perform work for you. Obviously, the less conductive your medium, probably the more resistance you're going to make, the less able that current is to effectively travel through your circuit. So this is just kind of illustrating that electrical resistance tends to decrease as your electrolytes concentration increases. Also, you get a lot of electrodes in your electrode potential, because remember, you are basically artificially retaining electrode potentials that are not what is naturally or spontaneously inherent to the materials that you're using. So you have to constantly fight to try to maintain those artificial electropotentials. And there can be a lot of fluctuations. Some of it's from your power source. Again, ripple tends to be kind of a big factor in trying to make sure you have a constant amount of current that is being fed into your artifact. That conversion between an AC power source to a DC power source, you can lose energy that way. That can cause fluctuation. You can also get fluctuations a lot in terms of based on the composition of your artifact, because we're not dealing with a solid piece of metal in most instances. There may be some core metal or core of metal iron, for example, but you also have a lot of material that is technically a mineral. It is technically a corrosion product, which has different resistances, more or less, in terms of its ability to conduct energy than solid metal would. And also the preservation state of your artifact, how fragile it is. Obviously, I alluded to this earlier, but if you have an artifact that is very fragile, there's a lot of cracks in it, it can't really withstand necessarily a lot of energy being fed into it. You can get a lot of, you can get a lot of problems with that because there's gaps essentially in the surface area that it's trying to pass through. Or
current density. AI is a great application for optimizing the current density.
yes, I don't. I'm sure that it could be, and I'm sure that there are. I'm sure. Right, right. I don't know if it's quite made it into our end of the field, just because again, it's still pretty new. And I'm sure that there are some labs probably out there experimenting with it. I'm sure, like on the industrial end of things, companies that do electrolytic reduction as part of electroplating or other types of more large-scale manufacturing activities, I'm sure they are definitely probably on board. I can't say for certain. I haven't actually looked into it, but I would imagine that would potentially be a good use of it to try to optimize this level. Yeah. And yeah, so these are all factors that essentially affect your current density, which in turn affects the efficiency of the treatment that you're performing. And also current density is also really important because being able to modulate that or adjust how much energy you're putting to the system allows us to perform different types of work at different times. So you can actually there are different levels, wrong button. There are different levels of current that are better suited to perform different types of work. Some of those tasks that I mentioned earlier. So low current density is primarily used for reduction. So essentially the lower currents are actually really good at just doing basically establishing that electrode potential for the material and sort of doing that baseline reduction, which is sort of the core of what electrolytic reduction is for. So it's that transformation of corrosion product into metal or other types of corrosion products that are more stable, and it is consolidation of fragile surfaces. Medium current is really good for desalination, so helping to drive those diffusion currents basically by maintaining a really good electrochemical, really stable electrical gradient that pushes those chemical diffusion gradients. And then high current density is what we would use to produce lots of hydrogen gas. So this would be essentially the settings you'd want to target for if you were trying to use electrolytic reduction as a way to clean your artifact. For the most part, we only really kind of use low current density and medium current density in most archaeological conservation treatments because these are sort of the two treatments that we're really going for at this point. Cleaning, we often take care of prior to doing electrolytic reduction for several reasons. One of which, obviously, the more concretion you have, the less conductive your material is. So you actually affect your current density by having a lot of this very porous, very kind of aggregate material that's made of all kinds of different things, and it doesn't have a very good, steady current density, doesn't conduct current very well, and also affects your current density because it's having to pass through all kinds of different materials at once. So we try to debulk these artifacts as much as we can and actually manually remove that concretion or that overburden before it goes into desalination or electrolytic reduction, just because it doesn't really help us because at the end of the day, achieving the chemical stability through desalination and consolidation and reduction are kind of what we really want out of this process. The cleaning is just kind of a bonus. So these are the two factors we're kind of really focused on. Also, there's a problem with high current densities is that sometimes you're not always removing the material that you want to remove. Sometimes you are accidentally removing material that you would like to keep. And that has to do with the nature of the material itself, and that a lot of times our base metals, the corrosion that there are certain layers that form on them first that are representative of what we call the original surface. So these are they're as close as we can get to what was once there in terms of the original surface of these artifacts. Yes, they have corroded, they are mineralized, but often they still retain information that is useful, whether it's just that boundary between what is sort of overburden and kind of removable material and what is material that we want to keep. And also, a lot of times there is still surface detail that is actually almost fossilized or trapped, kind of memorialized in that corrosion layer. So even though it's not metal anymore, it has detail in it, it has markings, maker's marks, things that we want to keep, things that interest us because they tell us information about this artifact. And some of those layers can be very fragile. What happens with cast iron is a alloy that is primarily made of ferrite that has been highly refined and then mixed with carbon. And what happens as cast iron corrodes is that carbon sort of separates out from the iron and forms its own layer. It basically forms graphite, which is what this is here. So we have what we call a graphitization layer, which tends to form on top of kind of the highest layer of corrosion that forms the boundary between what is artifact and what is not. And a lot of times there's some really, really important detail that gets trapped on these. Things like decorations, things like maker's marks, other types of touch marks that can help us really identify where these artifacts are made, who made them, where they came from, etc. So we really want to keep that information. Unfortunately, this graphitization layer is often very fragile. So what happens is that you have your production of hydrogen gas, and it tends to get caught in all these little pore spaces and imperfections, which, yes, also removes your concretion and your overburden, the stuff you want to remove, but it can also remove your graphitization layer and actually break your artifact into pieces, and you essentially lose a layer that you would otherwise really want to keep. So that's one reason that we often don't use high current density on these as well. It's just the risk tends to outweigh the reward for the most part. And honestly, like AI would be a good way to monitor things. Honestly, we mostly kind of eyeball it for the most part. We kind of pick current density based on the type of treatment action that we want to perform, how robust our artifact is versus how fragile, what it's made of, is it cast iron versus wrought iron, and then we essentially kind of judge the current density by how much hydrogen gas is being produced. We want basically just enough that it's producing some hydrogen gas that we know it's working, but we don't want to be producing a lot of bubbles and therefore having too high a current density. And this is something we do need to actually watch as the artifact is, as this treatment progresses. A lot of times the current density increases as things like electrolyte concentration increase and other elements of this treatment. So a lot of times we'll start the process at a much lower current density, and then it'll end up kind of slowly creeping up as the process goes on, just because of changes that are happening, because the process is working and it's changing things like conductivity and resistance and the nature of the material that it's passing through, and also sort of the nature of the solution it's in terms of there being, because obviously there is more and more, as things are breaking apart at the anode, for example, there is more and more material being dissolved into our medium as electrolytes. So that is something we need to eyeball to make sure we don't accidentally break the artifacts that we are otherwise trying to protect and conserve. And this just kind of said this a little bit about electrolytes and pH. In terms of that electrolytes, we really kind of need to control our electrolytes because we need them and able to have our current, but we also don't want them to get so concentrated they start to kind of precipitate out of solution, or they start to kind of gunk up the workings as well. And also we want to control our pH as well. Because these artifacts are mostly made of iron and they're sitting in water baths, what tends to happen is that we tend to still get corrosion that happens to these artifacts. So in order to essentially make sure that these artifacts are not, that our cathodes, essentially the artifacts that we're trying to actually conserve are not basically corroding faster than we are conserving them, essentially, we also want to make an environment for them that is passivating. And that basically means where corrosion essentially stops. And we do that by controlling the pH of the environment. So this is a fun type of graph that shows you essentially the conditions that need to happen to reach a pH at different pHs where passivation of the material happens, or basically where oxidative corrosion or corrosion from just being in contact with water essentially stops or slows down so it's not appreciable, and so that it's not out-competing the reduction reaction, essentially. Hopefully that made sense. Yes, and again, it's all about electrons being passed around. And so after electrolytic reduction, so we have taken our artifacts out of, so it's electrolytic reduction is finished. We've broken down the cell. Our artifacts look nice. They're as desalinated as we can get them. They're nicely consolidated. They seem much more physically stable, chemically stable, et cetera. What do we do then? Well, first of all, they've been in a solution that has a lot of electrolytes in it and is also very high pH. So we need to neutralize them. They then go through a series of rinsing baths, where essentially we then try to desalinate them again and try to remove, basically neutralize the solution, so that lower the pH until it's neutral, essentially, as well as remove any additional salts from our electrolytes that might have gotten in there. We also need to remove any sort of flash corrosion that happens during this process, because we will, since we remove them from an alkaline solution that is passivating them, we will get some flash corrosion, so we remove that. And then, excuse me, and then they go through a controlled drying process, which is really important as well. And essentially, we very slowly remove the water content, usually by putting them through a special dehumidification chamber or using desiccants or something like that, where we can really kind of incrementally draw out water from these artifacts. Sorry? We can. It just depends on what you have in terms of resources. Vacuum, we tend to use vacuum more for organic materials that have been desalinated, just because they tend to be more fragile and structurally, and the osmotic pressure that is exerted on them when evaporation happens is a lot greater when it happens here. This is basically doing it slowly is kind of more of a way to, one, you don't want to dramatically change the environment that an artifact is in, because that change itself may trigger new corrosion or new degradation processes, and also just sort of the slow removal of that water. Not only does it help to sort of come to acclimate better, but it also kind of prevents a lot of the flash rusting or a lot of the kind of after treatment corrosion that we might see on these artifacts as well. And then we want to think about how we're going to protect these artifacts long-term going forward, in terms of they are continuing, depending on how well our desalination or electrolytic reduction treatments work. Because unfortunately, unless we literally destroy the artifact after the fact and digest it and can measure the chloride content in it, we don't really know how, like if we've totally desalinated, we don't know if we've gotten all the chlorides out, for example. We don't know how good a job we did, essentially. So we always anticipate that we got as many chlorides out as we could from these artifacts. We've stabilized them as much as we could in terms of kind of reversing oxidative processes, but we can never really effectively tell how good our processes are. And we always kind of assume there's going to be some salt left in these, there's going to be some instability here. They're always going to continue to interact with their environment and go through corrosion processes, as long as they're in contact with oxygen and water and salts and other factors that essentially promote corrosion activity. So in order to reduce this likelihood, kind of retard this process, what we do is that we often apply some sort of barrier treatment to the artifact. So it can either be a chemical barrier, which is we basically take something like tannic acid or benzotriazole on copper alloy materials, and what this material does is that it reacts with chlorides that might still be in the artifact on a superficial kind of a surface level, and actually creates a precipitate. So it actually forms an insoluble compound that then sits on the surface. And yes, it changes the color and appearance to some degree. If you ever see go into a museum and you see that really kind of dark color on a lot of cannon, that's probably because it's been treated with tannic acid, and that dark color you're seeing is actually a solid precipitate that has formed on the surface through a reaction between the tannic acid and chlorides in the material. And so we might do something like that. We call that kind of a chemical barrier, and that will basically impede the ability of oxygen and moisture to essentially come in contact with the underlying metal, so the stuff that we just conserved, essentially. We also might use other types of coatings, sometimes things like paint systems. A lot of times we use acrylics, essentially just put on very thin coats of some other type of material that itself ages well, doesn't deteriorate in a way that, as far as we know, affects the artifact, and then otherwise is able to, again, impede contact with oxygen, moisture, other types of factors that would promote corrosion or other types of decay. And then these are lifelong commitments, these artifacts. We are always having to look out for them, take care of them health-wise. They will never not be in a position where they don't need some sort of monitoring or potential conservation. We can essentially do a lot, just like you can in terms of preventative health, trying to prevent health conditions with our artifacts by controlling the environment as well. So we invest a lot in environmental controls in terms of things, in terms of controlling the humidity and keeping, reducing the amount of moisture that's in the air, for example. Sometimes you'll have things that are displayed in actual oxygenless vitrines or cases where basically the air has been replaced by an inert gas, essentially. Or otherwise just sort of storing things with desiccants or other things that can more kind of actively or passively sort of try to control the environment that they're in so we get the best outcomes we can for as long as possible.
Will you ever have to do it like continuously?
Sometimes, yes. They're not always, but there are definitely examples, especially, if we went through a process, not to, again, a lot of this comes down to setup, but because so many artifacts are treated batch like this, they're not always effectively desalinated or perfectly reduced and consolidated. So these, and particularly, we often have perennial problems with them. They will often need to be retreated or treated. Maybe we might have to switch gears and do something else to them. Prevention and trying to control the environment is the best thing we can do sort of post-treatment for them and try to reduce how many times we have to do that. But they're just things that are kind of out of our control as well. The HVAC system breaks and all of a sudden the humidity rises. There's not a lot you can do about that immediately. You just kind of have to know what's happening and then try to correct the situation as best you can and keep an eye on the artifacts to see if there's any continued corrosion or other types of deterioration are occurring. Good question.
Maybe you can, for your setups, treatment habits. For your program that cost, what's the cost? Perhaps we are.
Mm-hmm. Yep. And it really depends. I mean, luckily, we try to avoid doing this as much as we can, or we really limit the number of artifacts. Obviously, 3 artifacts are probably going to have better outcomes than having 30 of them. Yeah. Right. And again, electrolytic reduction is not always the best answer for all the artifacts for that reason. We used to do electrolytic reduction on nails, for example. Sometimes we still do, but that is an example of you have hundreds of little tiny pieces of wrought iron nails. That the only really kind of effective way or cost-efficient way of doing it is to do a batch treatment like this, but you often get outcomes that then only last for a certain number of years before you start seeing problems. So yeah, and so in which case that would probably not be worth that treatment, and we might pick a different type of desalination treatment. We might just do them passively. We might, instead use a better alkaline solution that's stronger, using sodium hydroxide, for example, which can have a similar effect in terms of desalination by providing a very strong chemical gradient, basically electrical gradient for those chlorides to be attracted to, because that sodium hydroxide environment is so powerful in its own right. It creates that sodium ions obviously are really attractive to chloride items, or else we wouldn't have sodium chloride. So sometimes we can do it that way, and it's just passive. It just takes longer. We will use passive means, particularly for things that are fragile, or for things that this would not be a cost-effective method of using on them. It works. It just often takes longer. So, but good question. Anyone else? All right. Well, thank you very much for listening to me blather on. Hopefully that was somewhat coherent. I haven't given this presentation in a little while, so I've tried to simplify it a lot, but sometimes I
appreciation for what it is.
Yes, all right, thank you. And also just want to do a shout out. Our next Maritime Heritage Series lecture will happen right here at Fort Macon on June 19th at 11 a.m. and it'll be given by my friend Christine Brand, who's been running my tech back there. It's titled "Trying Woman: A History of Women in the Whaling Industry." It is a very interesting social history. I definitely recommend attending it. So, yes, very different. But if you have any questions for me, I'm contactable. I can definitely give you my email address. You can find me on the North Carolina Maritime Museum website as well. So happy to try to answer any questions.
Now, who do you work for? Private or?
I work for the North Carolina Maritime Museum, so I am their conservator, so I work for them. But I work pretty closely with other labs.